but it's an estimated W dot. However, in theory, if you have a no noise, everything is perfect. Your model is perfect. For example, your model 0, 1, minus 1, 0 is perfect. Your input matrix 1, 1 is perfect. And your measurement equation here is perfect. Then your estimate one, this will be the true one. This will be the true one. But when you have noise, then your estimate one won't be true one, but it will be close enough to your true state. That's what it means. So when we have like a displacement, and when we have like a power placement method, or we have optimum control method, we need state estimator. We need this called state estimator to estimate the states you don't have. The computer, this computer is going to compute the estimated state and estimated state derivative for you to feedback, because my feedback, I need this W dot. Understand? So this is only the two-state case. You mean W and W dot. Some system, you might have 50 states, you might have 100 states, you might have 60 states. That's a lot of states, and you have only one measurement. And for that case, that one measurement has to estimate the another 59 states for you to feedback. Okay, like this building may have 100 states, but I have only measurement on the top. So that's only one measurement. So that measurement will allow me to estimate all the other 99 states through the state estimator. Understand? So the power placement technique or other technique you are going to learn soon, they're all state feedback. As long as you have a state feedback, as long as you are short of your measurement devices, then you need the state estimator to estimate those states you don't measure. Understand? Okay? All right. So that's, I show you this this chart that you understand about the importance of state estimator, and some people call them observer. Anyway.
For the W, which one will we use?
For the W, which one to use? That's good questions. As a matter of fact, in real case, you can use either one. But we all use the state, this head. We don't use the true one. Because this head and W dot head all give you the same level of the error. And that, in theory, we can prove that as long as your system matrix A, B, C, D are good enough, then they will be stable. All right? It's a good question. That's a good question. I think everybody, I forgot to mention about that. So the question is, should I use W or use W head for my feedback? Normally, we use all the head together. That's normal. But however, you're allowed to use W if you want to do that. But W head already cleaned out some of the noises. In theory, that W head will avoid some of the noises or uncertainties from your devices. So this is why the optimum observer they call common filter. The common filter will filter out some of the uncertainties and noises. Make your W head and W dot head more smooth. That's what it means. Right? Understand now? So in practice, W head and W dot head are cleaner then W. Yeah, because they are capable of filtering out some of the noises. Okay, so that's this. This just give you some idea about this. However, the observer doesn't have to be that big. The observer doesn't have to be that big. In practice, the observers, in most cases, like a common filter, they are not that big. All right, but the observer pole, and crosstalk pole, that pole, the observer pole. This is very good questions. Just ask. We need to be careful here. In practice, I'm going to talk about it in practice. Now, in practice, observer pole are not necessary to be that big. That means eigenvalues are zero. That's in practice. Now, of course, the zero eigenvalue, what does that mean, zero eigenvalues? You understand what does that mean? If pole is zero eigenvalues, if my state, my crosstalk pole all in the zeros, what does that mean? That means my damping is very fast, right? What do you mean the pole in the unit circle here? Now, on the unit circle, that means no damping. Inside the unit circle here, there's good damping because the length is short. Maybe that's good size damping. Here, what does that mean out there? Zero. What does that mean, that zero? That means e to minus how much? Oh well, it's not e to minus. This is discrete time. The discrete time, the r is r equal to e to minus lambda t. LT. And if this is zero, means lambda equal to what? Infinity. That means your damping is infinity. All right. So that's what we call that B. Because huge step will be just that. Like a bar, we have a bar squared is equal to 0, 0, 0, 0. That's the eigenvalue is 0. And that means in two steps, the estimate state converge to true state. Just two steps. Fast. It converges to true state. And that's that's good, because if we can do that, that's good, because we need what? We need this head and that head to be true one. Because if this head and that to be true one, that means our closed loop control is approaching to our desired closed loop system. This, we hope this is a true one, right? We hope this is true one. This head, we hope this is true one. So we hope that our observer here, as the state converge to the true state as fast as possible. Understand? So if we can have that be, this is the extreme case. If we can have that be, that means the W hat and W dot hat will become, that means W hat and W dot hat will become the true W and W dot in 2 steps for this case. So that means what? So that's the question was asked, that should we use W or W hat? If I get that B, it doesn't matter. For this only 2-state system, in 2 steps, I will get the true one. So either you use W or W hat, it doesn't matter, because this will become true one. If my pole, if my observer pole is W pole. Understand now? Okay. So, however, now if you are noises, system noises or measurement noises, now in many cases that you may not get a dB for your observer, then what can we do? But we need to have W hat and W dot hat as close as possible to the